I'm going to start off by saying a little bit about what this complexity science thing is. I'm going to give just a quite general introduction to the idea of complexity science as applied to social policy, or to policy. And I'm going to talk about complexity in terms of these four themes, or these four bits of jargon, just to give you an idea of the theme that underlies pretty much all the things that you're going to be hearing about today. So I'm going to talk about the fact that society is multi-level. I'm going to talk about the idea of non-linearity. I'm going to show you the idea of emergence, and throughout all of this we will all see lots of things about networks. So, what do I mean by all of these words? Multi-level. Well, the idea here is really quite straightforward, but somewhat or often difficult to apply in particular situations. The idea of multi-level is that society consists of everything from neurons, individuals, crowds or collections of people, through to institutions. And when we are thinking about policy or understanding society, one of the difficulties is that we need to think about all of these levels simultaneously. That what happens at the individual level has an effect at the institutional level, and vice versa. But what happens, obviously, at the level of institutions, of government, of church, of state, has an effect on individuals. So we have a complicated system where we have what's called both upward causation and downward causation across these different levels. And that's one of the fundamental issues in the idea of complexity science. Then there's non-linearity. What do I mean by that? I guess for many of you, you'll have, in your degree, you probably did some statistics, and you did things like regression and statistical techniques like this. But even if you didn't, the idea of linearity is straightforward. The idea is that something is affected by a number of other things, and the amount that that thing is affected by depends on the changes in those other variables, those other things. And in particular, that a small change in one of the factors is likely to end up with a small change in the dependent variable, the effect. A big change will have big effects. Now, this is what I and others teach our undergraduates about. Unfortunately, it's not a very good reflection of the real world. In the real world, the opposite is often the case, that small changes have huge effects. Big changes may or may not have big effects. And it's that I'm getting at when I talk about non-linearity. Here's an illustration of non-linearity, and I promise that this is the only mathematical equation that I'm going to be showing you today. This is what's known as a logistic growth equation, and I use this as an example because this is a clear example of a relationship that is non-linear. In fact, it grows like an S shape, as in the graph. This particular equation comes essentially from ecology, but it applies quite well to things that are more social. For example, if you plot the diffusion or the spread of mobile phones from when they were kind of those brick things to the state where we are at the moment, when there are more mobile phones in the UK than there are people in the UK, then the shape of that growth curve looks like this S shape that I've got there. And indeed we can build a simple little model of such diffusion. It goes like this, and as it spreads, that kind of spread applies to all sorts of innovations, to the spread of rumours and gossip, to the spread of mobile phones, to the spread of things like whether one smokes or not. So in many circumstances in society we have to deal with non-linearity rather than nice simple linear relationships. Here's another aspect where what we see appears to be more complicated or more complex than might at first appear. Let's imagine that we have a couple of people. We'll call them technically nodes in a network, but you could think of them as people who know each other, who are friends. We say that they're connected with an edge, and there you can see in the middle of the black square there are two people, little red dots, and they're linked together by, let's say, friendship. Now let's add some more people to this world. And we're going to do that, and at the same time we're also going to get these people to get to know each other. We're going to put more links in our world. And we're going to do that using a special sort of rule. That rule says that when new people are introduced or new nodes are introduced, we create links or friendships, not just at random, but preferentially, such that the popular people, the popular nodes, are more likely to have a link to them. And we get this rather pretty looking pattern. You can see there, you can see it growing. The size of the dots indicates the number of links each of those nodes have. And there's something kind of interesting if we plot what's going on here. If you look at the top graph, the one that's called degree distribution, you'll see that most people have just one link. They only know one person in our diagram. There were a few, the big red dots, a couple here, who have lots of friends. Remember the rule that we're using to make the links. So it's a very non-linear relationship. It's a very non-linear curve we've got there. Intriguingly, however, if we take the logarithm of both of those axes, you end up with the bottom graph. And as you can see, the points on that graph more or less follow a straight line. This is an example, a simple example of what's known as a power law. And again, it's a characteristic of many relationships, many features of actual societies. I've talked so far about nodes and links and friendships and people, but let's have a look at a few more realistic examples. So power laws in general are often found where we have a few exceptionally popular items, the big red blobs in my previous picture, some averagely popular items, but the majority of the items, whatever they may be, are relatively unnoticed or unpopular. So, some examples. About 50% of scientific papers that are published are never referred to and never cited by anybody. This is very sad for us academics. If you look at the revenues of Hollywood movies, there's a few blockbusters, and most of them go straight to DVD. If you look at websites, well, Google gets an incredible number, and my homepage gets very few. Phone calls received per day, even the size of firms, the number of employees of different firms, they're all related in this power law kind of way. So that's another aspect of complexity. Here's a third or a fourth. You may recognize this. It's not actually the M25, but it could be. What's happening here is that a bunch of car drivers have been told just to follow the car in front. And do you see what's happening? Even though there are no traffic lights, no traffic accidents, there are traffic jams. And this is an instance, a nice example of what we call emergence. Here we have individual cars and their drivers who are following a simple rule, just follow the car in front. But what emerges from their actions is a traffic jam. Think back to in a moment what I've just been saying a moment or two ago about multi-level. Here we have one level, which is the individual car driver. And we have a superior level, which is the whole assembly of cars going round and round in a circle. And we have a characteristic of the whole thing, that is a traffic jam, which only makes sense at that superior level. You can't talk about a traffic jam of a single car. You can talk about a traffic jam on the M25. And that's also a theme in complexity science, that what we're interested in is the individual actions and also the way in which those individual actions yield, through emergence, complex behaviour at the level of the society, of the organisation, of the institution, or whatever. And one of the ways in which we can come to understand and comprehend that kind of emergence, and indeed all sorts of complexity, is to build a model of it. And here is a simple model of exactly what we were seeing before. We've actually got two lanes of cars rather than one. But if you look, you'll see that we're getting a traffic jam just as before. And we can adjust with this model. It's a nice thing about models, is we can adjust various parameters and see what effects those parameters have on the behavior of the traffic jam. Incidentally, notice that the cars are going in a clockwise direction, but the traffic jam is moving anti-clockwise. And if you get a helicopter and fly over the M25, you'll see that is exactly what happens there too. The traffic jam, as it were, goes backwards as compared with the direction of the traffic. Okay, so I've talked then about a few of the characteristic features of complexity, and I've illustrated those with respect to social phenomena. Complexity is an idea that has permeated the whole of the sciences, so that there are many people working on the complexity of physical phenomena, of biological, ecological, environmental phenomena. But what we're going to be talking about today is the relevance of complexities to social phenomena, in particular social policy. So just to summarize, the way we're thinking about things is that society and its components can be described as a complex system, a complex adaptive system, because there are many units in it, whether people, of course, and organizations, with links between them, of many different kinds, that the interactions between those units are important, there are feedback mechanisms, and that from all of that we get nonlinearity, emergence, the idea of multi-level institutions. In these few remarks, I've only begun to scratch the surface of what complexity science is all about. There's a great deal more that you'll be hearing about during this morning and indeed in the afternoon. But I hope what I have done is got you curious as to what these kinds of ideas can do when you are looking at policy and society.